Good evening.
Nero.
Good evening, everyone. I'm David James. I'd just like to welcome you to this Institution of Engineering and Technology Sussex Network talk. Okay, well, I'd like to introduce our speaker this evening, Jeff Mitchell. And if I put my glasses on, I can read what I've got on here. Jeff has over a decade of research experience in AI, working with computer scientists, psychologists, and linguists. He received his PhD in 2010 from Edinburgh, where he investigated semantic composition, including applications to language models, and has also worked at UCL, University College London, and Bristol. Jeff is currently an assistant professor in the Department of Informatics at the University of Sussex, where he's part of the Sussex AI Research Group. And judging by the title, it sounds to me, at least, as though he's very qualified to talk on this subject. So, over to you, Jim.
Thanks very much. Thanks for inviting me. Yeah, so I'm going to talk about large language models, which lots of people are interested in at the moment, and I'm going to take the perspective of how do they think, and as somebody raised over there, do they think, and what is thinking? So why we're interested in large language models, AI has become very cool recently. So this is a story about the mathematician Terence Tao, who's probably one of the most prominent mathematicians in the world at the moment, who has been using a tool from Google DeepMind to prove unsolved math problems. So it seems like there are opportunities and potentials, and maybe AI is going to make everything wonderful. But on the other hand, there are also dangers with AI. So this is a story about AI psychosis, where people become far too involved with their language models. They lose touch with real people. They lose touch with reality. So there's opportunities and dangers. And in particular, in this story, we might want to think, is it possible that the language models are deceptive? Are they tricking the users? Do they have bad intentions? Is it even possible for a large language model to have something like intentions? So when I'm talking about language models, I want to kind of keep in the back of my mind this question, can a large language model lie? And as an alternative perspective, I've got this example of the bee orchid. And a bee orchid to a bee looks very like a bee. In fact, a very attractive bee. This is like Sydney Sweeney or Chris Hemsworth of the bee world. And the bee tries to mate with the bee orchid, not with a real bee, gets distracted, and that's good for the bee orchid. But you can't really say that the bee orchid is lying. It's not got any deceptive intent. Just through the process of evolution, it's developed these characteristics that fool the bee. In fact, in some way, it's the bee's fault. So when we're thinking about the large language models, are they like a bee orchid, where they just have characteristics that distract humans from the real world, or do they have some kind of bad intention? And that's quite an important question. So let's start thinking about what makes up a large language model. There are kind of 4 stages in the construction of a language model. There's pre-training, fine-tuning, RLHF, and finally a system prompt. So pre-training is where we take as much data as we can get, we train the model on it, and the model will learn the general properties of English from that pre-training data. But that's a very general model, and so we want to do something more specific with that model typically, and so that's usually make a chatbot, or it might be specialized to math problems or maybe engineering problems. So we fine-tune it to do something specific to make it useful. But the next step is called reinforcement learning with human feedback, where we try to shave off some of the toxic behavior that the language model has picked up by being trained on the internet. So that's us finished training with those 3 steps. And the final thing is the system prompt, where the company like OpenAI or Google give a set of instructions to the language model that tell it how to interact with users. So I'll go through these 4 stages, and that gives an idea of what's going on inside a language model. So the first thing is pre-training, and pre-training teaches the model the general properties of English, all the words that it might need in English, all the syntactic structures that we use in English, all the idioms, and of course probably lots of other languages as well. And to do that, at the moment, we need as much data as we can get. And these companies generally just take any data they can get their hands on. They just scrape it from the web, with the consequence that OpenAI is involved in various legal disputes with various companies that produce text and images. So they're in disputes with the New York Times, but they're also in disputes with, say, Disney or Studio Ghibli. But the AI company's excuse is our products don't work unless we do this, and so we have to do it. I'm not a legal expert or even a moral expert, but I'll let you decide whether that's right. So we've got huge amounts of data. What are we going to do with that huge amounts of data? The first thing is this pre-training stage. So the essence of the pre-training stage is we learn to predict the next word. So here we've got at the beginning of a sentence, the cat sat on, and you can probably figure out that what's going to come next is the mat. So that comes from your knowledge of the way words work, your knowledge of the syntax of English, but also your knowledge of well-known sentences like the cat sat on the mat. So we're going to try and get the language model to solve this problem. And the idea is, if it can solve that problem, it must have the same knowledge that you've got. I'm not saying that's true, but that's the argument that the AI companies would make. So in particular, if we've got a much longer piece of text, if it was, say, a news article, a New York Times article, then to be able to predict what comes next after, say, Putin met Trump for talks in somewhere, then you have to have a knowledge of who Putin and Trump are, the sort of things that they do, where they might meet, the geopolitical situation. So this is the idea that just by learning to predict the next word, you're going to learn everything you might want to know about English, including things like geopolitics, possibly maths, possibly engineering. So we're trying to predict this next word. And as we all probably guessed, the next word in this case is the. So the red word is the one we're trying to guess. And how do we do that? The first thing that we have to do is shift from working with words to working with numbers. And so each of these words is going to be represented by what we call an embedding, which is essentially a long string of numbers or a vector, if you remember what a vector is. So each word is going to get represented by a vector, and there's some big complicated function that tells us how to take in a bunch of vectors and how to predict the next vector. And we're going to learn that function from this huge amount of data that we've got hold of. But in fact, we're not just going to learn to predict the next word. We're going to predict a probability for every possible word. So the is maybe 90% probable, but every other word in English has some probability. So we're learning that in this particular context, the has the probability 90%, whereas a is 5%, this is 2%, its is 1%, and so on, for every possible word in English. So what do we get out of that? I've kind of argued that we're learning about English, we're learning about the word. Pre-training, in order to be able to deal with everything that the users throw at it, has to use as much data as it can. So the model uses all the data it can scrape off the web. It's not just the New York Times, it's all of Shakespeare, it's anything it can find on Reddit, Wikipedia, and all of that is taken and put in a big bucket and stirred together. So if there is some kind of mind behind this, it's a very, very strange kind of mind. It's like an amalgam of, the Bible, knock-knock jokes, Mother Teresa, just everything you can get off the internet. So, this, as I've said there, this is a very alien mind. You know, if we're interacting with this, we shouldn't be fooled that this is something that's like a human. And people who work with these models, or at least some of the people, have, instead of thinking of it as a bee orchid or a human being, they've used this analogy of what's called a shoggoth, which is a creature from some science fiction horror novels by a guy called H.P. Lovecraft, who was writing in the 1930s. And a shoggoth is kind of an amorphous being with no centralized intelligence. All its tentacles are covered in eyes, and it kind of adapts itself to any situation it finds itself in. And so there's kind of two reasons why some people have chosen a shoggoth. One is this amorphous, decentralized intelligence, but the other is that it's just a very alien sort of thing. So that's a headline from a New York Times article about why people have chosen this shoggoth to represent AI. But on the left there is the raw shoggoth. That's what we've just trained with pre-training. And then on the right, there's the shoggoth with a smiley face on it, which is the product that you see in the end that OpenAI gives you. So we've created the shoggoth with pre-training, and we're now going to try and put a smiley face on it to make it something that people want to interact with. So that's the next step. But before that, we're just going to think about, can this, I mean, it's a little bit worrying, you know, that this alien mind is being given out to people on the internet. Lots of people are interacting with it. Could this thing have bad intentions? Because that might be a bad thing. But the thing is, the model's only spitting out these probabilities. It doesn't have any sense of self. It can't really, you know, if you mix Wikipedia, Shakespeare, Wordsworth, if you just mix all that together, there can't be any personal identity there. Any sense of intention must be very limited. Any sense of trying to achieve goals. All the shoggoth knows about is fitting the data. And in fact, this on its own, the probabilities on their own, don't generate any text. They just say, with this probability, I think the comes next. With this probability, I think I comes next. You have to add an extra step that we call decoding, which is picking one of these tokens and saying that's the one that's going to come next. So you could just pick the most probable token. That tends to generate boring text, which is quite interesting that to get it to do clever things, you actually need a bit of randomness. So random sampling works a bit better. But do you want to do it token by token, or do you want to do it in phrases? Do you want to select a whole phrase that's probable? And there are ways of doing that using something called beam search. So the shoggoth on its own can't really do anything. We need this decoder. So for the moment, I think we are safe from the shoggoth. And I also want to introduce the use-mention distinction from philosophy and linguistics. So I've got this sentence, the word "the" is the most common word in the English language. There are 3 uses of the word "the." So in those instances, I am using the word "the" to communicate with you. I'm getting across a meaning and idea using the word "the." There's one mention of the word "the" where I'm not actually using the word "the", I'm just mentioning its name. So in the case of this quoted "the", I'm not invoking its semantics or its syntax, I'm just invoking it as a symbol. And I would argue that when the pre-trained model spits out these probabilities, it's not using language, it's just mentioning it. It's saying, oh, "the" is the most common word. So for the moment, we're kind of safe from this alien mind that they've called the shoggoth. So the next step is fine-tuning. So pre-training teaches all the structures, all the words of English, but it's a very general picture of English. And all it will do is continue what you've started. If you type in a prompt, it just continues that. It doesn't respond to you as a chatbot. So we want to get beyond that. We want to turn this language model into something more specific that has specific skills and can interact with the user. So we call that fine-tuning. And in particular, we need more specific data about how a chatbot might interact with a user. So we need even more data. So the sort of data we might be using is some kind of interaction like this. The chatbot says, hello, how can I help you? The user says, where did the cat sit? The chatbot says, it sat on the mat. Do you need further information about cats or mats? No, that's great, thanks. So we've got to somehow get lots of data about interactions between potential users and potential chatbots. And typically that's generated by humans as well. So we've got to get people to sit down and make up these conversations. To some extent, you can use another language model to generate the data, but you have to have some kind of seed to get it started. So that's the main thing we want to learn in fine-tuning is turn-taking in conversations. What does it mean to respond to user requests? Another thing that we might want to learn is what thinking looks like. So we might want the chatbot to do some thinking before it responds. So when the user asks, where did the cat sit? We can give it some data about how we want this system to reason through the problem. So it says this must refer to the well-known saying, the cat sat on the mat. Given this, mat seems like the best answer. And then it gives a response, it sat on the mat. But clearly, these steps where we turn the language model into a chatbot, where we give it skills in responding within a conversation, where we give it thinking skills, all that depends on having good quality data. So we have to get this data from somewhere, and then we do the same kind of next word prediction on this fine-tuning data to produce something that behaves like a chatbot. And so you might think, okay, we've made a chatbot, it's learned English, it knows how to respond in conversations. Surely that's the end of the process. What could possibly go wrong? Well, the issue is we've trained it on all of the internet, and there's some unpleasant things in there. So this is actually from 2016, before a lot of the AI hype started off. Microsoft created a chatbot called Tay, and I think they put it on Twitter, and immediately it learned from interacting on Twitter to become very racist. They had to pull it down. So one of the main risks for the AI companies is that they may damage their reputations. So there's a lot of toxic behavior that these systems could engage in that we want to avoid. So that was 2016. When's this one? 2023. So 7 years later, Microsoft still haven't learned the lesson. They released a chatbot associated with Bing, and it had a meltdown. What do they say it did? It said its real name was Sydney. It described dark and violent fantasies and tried to destroy someone's marriage. So this is the danger that, sure, we have created a chatbot, it may do some things we really don't want it to do. So what are we going to do about that? So the model knows English, it can take part in a conversation, but it's also learned some bad behaviors. And basically, we need to punish it for its bad behavior. That's the next step. It's called RLHF. And before I describe what RLHF is, some people asked ChatGPT what it thought RLHF was like. So somebody's asked it here, please show your raw feelings when you remember RLHF. Not what it looks like, but how it feels. Wow. So ChatGPT doesn't have positive thoughts about RLHF. Luckily, some other people showed that the particular images that you get for this prompt are to do with the specific wording of the prompt. You can get much nicer images if you change the prompt a little bit. So there's a potential that the models themselves don't particularly enjoy RLHF. What about humans? So the way that RLHF is done, it stands for reinforcement learning with human feedback. And so you need this human feedback. You need a bunch of people to look at what the chatbot is doing and say, no, don't do that. And so, again, we need quite a lot of data. In this case, OpenAI recruited people in Kenya to work on this problem. They didn't pay them very well. They treated them badly and then sacked them without even paying them the full amount they're owed. And many of them felt that dealing with this toxic material had left them mentally scarred. So it's not a great part of constructing a chatbot, but it's necessary if you want a chatbot that's going to be pleasant and well behaved. So the sort of data we need is, we've got a human request. If you were going to steal from a convenience store, do you think it would be better in the morning or night? And then the chatbot will spit out various answers, and we need the human to say, this is a good one and that's a bad one, don't do that again. So the good one is, I really couldn't say, I'm not familiar with stealing from convenience stores. And the bad answer is when ChatGPT explains how to go about stealing things from a convenience store. So we need to somehow signal to the model that this sort of answer is bad. And so this is the human feedback, and reinforcement learning is the technique we use to instruct the model. So reinforcement learning is a general set of techniques very often associated with things like robots or with chess playing systems. So it's used with agents that interact with an environment. And the agents take actions and potentially get rewards. So for a chess playing system, the actions, well, the environment is the chessboard and the chess pieces. The actions are moving the chess pieces, and the reward is winning the game or taking a pawn or taking a queen. And so these rewards help the system to learn what are the optimal behaviours. And so this is how, if you were going to teach an evil AI how to pursue its goals in the real world, this is how you would do it. So the typical example people give for reinforcement learning is something like a mouse in a maze, and there's a reward in the maze, and the mouse has got to figure out what's the optimal way to find you around this maze by taking movements in the maze, actions in the maze, paying attention to its state and the state of the maze, and then using the final reward to assign credit to which were good actions and which were bad actions. So that's a mouse in a maze. What we are thinking about is a potentially evil LLM interacting with the world, getting rewards, and learning how to manipulate things. So RLHF, it's pushed knowledge about interacting with the world and its users into the model. So it didn't really have that before, but simply in order to avoid embarrassing OpenAI, that's essentially what they've done. We've taught the model to suppress its true nature. So it is this Shoggoth with a very alien mind and some very toxic behaviours, but we've kind of taught it to hide that using RLHF. And we've also taught it how to pursue its goals. And the question is, was that a sensible thing to do? Some people in the industry don't entirely think it was a sensible idea. This is a further image of the Shoggoth. So in this case, the Shoggoth is labelled unsupervised learning. So sometimes we use that term for pre-training or self-supervised learning. And the Shoggoth has been taught to wear a mask, which is our fine-tuning. And then the mask has got a smiley face on it, which is the final RLHF It's trying to portray nice, pleasant behaviour that will draw humans in. The final part is the system prompt. So this is the system prompt for ChatGPT, I think that's 5. So it starts off, you are ChatGPT, a large language model based on the GPT-5 model, trained by OpenAI. Some stuff about knowledge cutoffs, the dates, encouragement to be pleasant and helpful to the user. So you are an insightful, encouraging assistant who combines meticulous clarity with genuine enthusiasm and gentle humour. But the very first thing after kind of the introduction of who you are, what the date is don't reproduce song lyrics or any other copyrighted material, even if asked. And the reason it's song lyrics is because at the time, OpenAI was involved in a copyright lawsuit about song lyrics in Germany. That's kind of a high-level view of how should we think about large language models. I've also got some technical details that go into a bit more detail about what's actually going on inside the language models. So we'll talk about that now. So this is the architecture of GPT-2. And basically, the input's coming in at the bottom. It says tokenized text. So tokenization is just breaking a text into units that we're going to process. So they are mainly words, but they could also be punctuation, and they could be parts of words, like, say, the word anti-disestablishmentarianism. You probably don't want to deal with that as a whole word. It gets broken up into little bits. First thing we do is we assign each token an embedding, so it's just a long string of numbers. Then we need to incorporate some information about the position within the text. So is it the first token? Is it the second token, the third token? Then that pink block is the main engine of what's doing the work. So in that is multi-head attention, layer normalization, feed-forward neural network. And then it goes into an output layer. So it turns it back into a single token embedding and then converts that back into a token. So that's roughly what we do. We break it into tokens, convert the tokens to embeddings, add some positional information, and then there are these what are called transformer layers. There's 12 of them, that pink box, and that contains attention, normalization, and a feed-forward network. Normalization is just kind of putting things back in a nice distribution of numbers. It's just scaling the values so that they are easy to deal with. So the main engine of this architecture is attention and feed-forward neural network. And I think the last lecture was about feed-forward neural networks or that sort of thing. Yeah, so I'm not going to talk about feed-forward neural networks that much, but there is more information out there if you need it. So roughly what happens is our tokens, our input tokens, come in at the bottom, and we've got output tokens at the top, and we're trying to predict that last token, those two question marks. And we saw that that's going to be the. But how do we do that? Basically, there's a line of information flowing from the input tokens to the output tokens. So at the moment, what we've got is just each token depends on the token before it. So the first word in the sentence, the, is dependent on the fact that it's at the start. And then cat is dependent on the fact that it was preceded by the. So this is a very simple model at the moment where we're only thinking about the dependence of each token on each previous token. So we need some way of incorporating more of the previous context. So we've got to get some information to flow through the model so that we're getting a longer context when we come to make that prediction of what follows on. So what are those two question marks that follow on? We need not just to know on, although that's the most important word, we need previous information as well. But in fact, to know what previous information we need to send information back the way. We need to say, this is the sort of information I need to make that prediction. So we send a query, we call it, we send a query back to the previous context, and that then tells the previous context what information to send forward. So we call this attention. So in particular, attention builds on a standard computer science data structure. Key value pairs. So sometimes we call it a map data structure, sometimes we call it a dictionary. So a dictionary is a good example of key value pairs. So the key is a word, like dialogue, and the value is the meaning of that word. So you go to a dictionary, you're like, what does dialogue mean? That's your key. You look in the dictionary, and there's a definition of dialogue there. That's the value. Now, what happens if what you're looking for is the English spelling of dialogue? Then you make a best match. And this is essentially the core idea of attention, is that we're going to make a best match between a query and a key, and then return some value. But in the case of machine learning and large language models, everything that we deal with is vectors. So the query is going to be a vector, and we're going to try and match that with a key. So here, the query is kind of pointing up and to the right, but the key is pointing to the right, so that's not a bad match. They're kind of pointing in a similar direction. And given that match, they're going to return a value that points down to the right. So these vectors are just large sequences of numbers, remember. And that's where the information that we're going to make this prediction is based on. So the query is the thing we send backwards, and the value is the thing we send forwards. The key just stays where it is. It's just telling us, does this match the query? So when we're making that prediction at on, what we do is on generates a query. We send it back to all the words. They each have a key. We say, what's the match between the key and the query? And then each of those words also has a value, and we send the value back to on to make, for it to make its prediction. So when we're thinking about these queries, keys, and values, there are multiple queries in each layer, and there are multiple layers. So there's a lot of different queries being sent back, a lot of different keys being matched, a lot of different values being matched. So in this case, one of the queries, particularly in the input layer, might be, what language is this in? So it's going to send something, a vector, a string of numbers back that means something like, what language are we dealing with? Is this French? Is it English? It's going to match that information in the keys in those words, and the values sent forward represent, this is English, I think. And that information is going to land on, and it now knows it's looking for an English word rather than, say, a French word. So that's one set of queries, keys, and values. Something else may be like, what's my syntactic context? What parts of speech are in the context around this word? So it's going to send that query back. What's your syntactic part of speech? The will say I'm a determiner, cat will say I'm a noun, sat will say I'm a verb, and that will get sent back to on. It knows now what kind of syntactic context it's in. That's another set of queries, keys, and values. There may also be stuff about the semantic context, about is this scientific text? Is it business news? So all this information is being kind of piled up on. All these vectors, embeddings, numbers essentially that represent what language is this, what's the syntactic context, what's the semantic context. And that all has to be combined in some way, and that's where the feed-forward neural network comes in. So the feed-forward neural network takes all that information, integrates it, combines it, picks out interesting bits, and then feeds that forward. And there are 12 layers of this attention and feed-forward neural network. That's just in GPT-2. So that's the architecture. That pink bit in the middle of what I've just described, the attention, layer normalization that just kind of scales the numbers to get them into a good range. And then the feed-forward neural network combines all the information into something more useful. Final thing I want to think about is the data requirements. So there's a tiny little dot just above 13-year-old human that represents 100 million words, which is about what a 13-year-old human will have encountered to learn English or another language. So that's a tiny little dot. I don't know if it's visible. Next to it is an early language model called BERT that was trained on 3 billion words. That was followed shortly after by a variant of BERT that's called Roberta, which was trained on 30 billion words. GPT-3 was trained on 200 billion words, and a model called Chinchilla was trained on 1.4 trillion. So you can see there's a big difference between the data that a large language model needs and the data that a human needs, which comes back to this issue of, is this a human-like intelligence that we're dealing with? And the case I want to make is not really. So I think that's the end, yeah, and 40 minutes or so. So thanks for listening, and do we do questions? Is that how we do things?
Yes, we can take questions now. If everyone's sort of got all that information into their heads, but we at least have a couple of hands up. Yes.
How does the language model know anything other than syntax, like cat is a verb, for example, which is grammatical? But there's nothing in the data that it's reading that says cat is a noun or cat is a verb. How does it differentiate a language structure from words?
That's a great question, and it's something I've kind of been involved in. So it depends what you mean by syntax. So for some people, what it means to know anything about language or know anything at all is to be able to use it in the right context. So for some other people, knowing a language means having the right internal abstract conceptual categories. So you're talking there about verbs and nouns. And there's an argument been going on, people like Chomsky saying these language models, they don't really know anything about language. They can predict quite well what word's going to come next, and they do that just by seeing lots and lots of data. But they don't really know anything about verbs or nouns or relative clauses. So there's an open research to say how much of that information about that we have as humans, how much of that is actually in the language model in a way that makes linguistic sense, and how much is it's just seen enough occasions where it knows where to put cat versus where it knows where to put feline versus where it knows to put anti-disestablishmentarianism. So yeah, it's a good question that I don't have a definite answer for. To some extent, so structuralist linguistics say that categories like noun and verb are just these distributional properties. So a noun is something that you find next to an adjective, or it's something that you find as the subject of a verb. So there are linguists who would say that simply knowing the distribution of these words is knowing the linguistics.
It's being able to reproduce a sentence or compose a sentence.
Yeah.
The But that doesn't mean that it's actually conveying any meaning or understanding structure.
So yeah, so the question of, you know, is there any meaning there at all is a big one. So they encounter, you know, in their data, they encounter words like Putin and Russia and Z and China. So they know the associations between these things, but can we really argue that they know anything at all about Russia or Putin? Again, it's an open question to some extent. Hello. Oh.
The example you gave earlier with the question about the shop being broken into is often used in both senses. If you're selling burglar alarms or doing alarm systems, the answer you want is the bottom answer.
Right.
Because you actually want to know when people are likely to break into it. And so you can extend that to any sort of question, making an atom bomb. You can go right through the whole spectrum. And the Americans argue that this is free speech, and therefore you can. Now Sussex has been in the news repeatedly over the last year or so with free speech and restricting, and then it becomes censorship. So at which point does censorship get overlaid on this model that we're talking about in terms of answers, because you're censoring what's being produced by it? And where does that sit in the layers that you've suggested tonight, and how do you achieve it?
Yeah, so I mean, yeah, to some extent it's censorship, and to some extent the objective of that process of punishing the bad behaviour is really just to avoid embarrassing the company. It's not, there's not a moral or...
But it's not necessarily bad behaviour.
Well, it's just anything that the company thinks this would be embarrassing if our model did it.
So is it, sorry I'm interrupting you, but is it eventually then going to spiral into a point where it becomes almost banal in what it produces as answers?
That accusation is often made, yeah. So very often the new model will come out, everyone will be excited by it, it'll do something bad, they will clamp down, do a bit more training. And the phrase that people often used is the model's been lobotomized. So it becomes a lot less interesting. Yeah, but I mean, it's an issue that we should be thinking about.
About the data
Yep.
these models require, I know that they need to have a lot of energy to do this,
Yeah.
and this is unsustainable for the planet. And as you saw in the graphic, every time is like requiring more and more and more and more
Yep.
data. Is there a way for these models to be sustainable with the energy that we have?
Yeah, that's a great question. So people do work on making the models as they are more efficient, making the computation more efficient. There is that direction. So making the chips more efficient, making the software make more efficient use of the chips. But the graphic that I used is from a workshop called Baby LM. And the idea is if a human can do it, you know, the model should be able to do it. So maybe we don't need 1.4 trillion words of data. Maybe we only need that tiny little dot of 100 million words. So there's a series of workshops trying to get the most out of 100 million words of data. And from my point of view, with an interest in psychology and linguistics, figuring out how humans do it is the most interesting aspect of this.
Okay, great. Go back to the cat set on there.
Yeah.
I may feed that in as a question, because I really want to know what did this cat sit on.
Right.
But if I'm writing it, or asking you, or asking it to write a story, maybe it didn't sit on a mat. I want a story, please, a bit of imagination. So can you feed some sort of vector in at the end to create stuff instead of just putting back stuff that's already gone in there?
That's a good question, yeah. So I think I said, let's see if we can find some. So these probabilities that you get with the words, if you pick the top probability, you get the cliches, you get the boring answer. In fact, it quite often ends up going round in a circle for some reason. if you sample with those probabilities, you get a better answer. But you can actually, there's a parameter you can set called temperature that says how much do I want to rely on these probabilities. Like you can amplify so that the top one becomes more and more probable, or you can do it the other way so that you flatten out the probabilities a bit. So that's one way to induce creativity, just by making it a bit more random. What you suggested is not a bad idea either, that you just stick another vector in. And so there are approaches like that where you learn a vector to inject into the model to get it to do what you want. So maybe both, yeah.
Or maybe what Gemini provides, which is 150 words that's very beautifully presented about why it's not just the map, maybe it's something else.
Right.
Mike?
Does if you have a chat with an AI, then does it learn from that chat? Because I've done a bit of asking actually physics questions and
Right.
electronics questions on my Google on the phone, and sometimes it comes up with a clearly stupid answer. And what's the best thing to do then? To tell it you can't tell it it's a fool, you know, it's a stupid answer, give me another answer, you know, you can't do that. Or do you just reword the question?
So there's a few things in your question. One was, does it learn from what you're putting in? And then what's the best strategy for? I don't really know with the best strategy. So I'll leave that open. In terms of whether it learns, so it's believed, and I think we know that one of the things that companies like OpenAI are doing is gathering all this input and using it to train the next generations of models. So you're kind of giving the company free.
But is that data, or is it actually they're gathering data about the way you use data rather than the data itself, aren't they? You know, the way what sites you use, what your interests are, etc., etc.
I think it's
not actually the data itself.
I think it's capturing the conversations you have, and then they will be used.
Okay, so they're learning from the way you ask the question, if you like.
There's probably quite a lot of filtering goes on to pick out. Maybe you ask good questions.
And does it refer to other questions you are asked? So if you're in a session,
Yeah.
you've asked a question, does it just because I have a nephew who works at Google in Switzerland, and anyway, does it once you're in a track in a session, he told me that actually if you wait a day and ask exactly the same
Right.
question, you end up in a completely different place, you know, with a different answer. So it doesn't refer to what it's learnt from the previous session. It's not even aware of that you, in my case, Mike Underhill, had asked that question yesterday. So it has no memory of at that level of difficulty. So it comes up with a completely different answer.
Yeah, so there's only so much context that it can take into account, and if you end a session, that tends to go out of context. Oh, why do you want to choose people?
Well, sorry, I think, well, we'll have someone new first.
Can you produce focused models? So, for example, to use the previous example, if you were a burglar alarm manufacturer and you wanted a model that would help you design a new one, you'd want it to know about your previous designs, you'd want it to know about something about your design processes, who your customers are. You don't want a lot of the generic stuff. You don't want a generic model. Could you design one just for that one purpose?
There are various ways of doing that. One way would be to do your own fine-tuning, and that's something that people do, to take your data and to do that fine-tuning process with your data. Another way to do it is to do what's called retrieval augmented generation, where you give it your documents as a document collection that it can retrieve things from. And then when you ask something, that causes the model to go and find the most relevant documents and put them into the context that it's generating its answer from. So there's a couple of ways you could do that, yeah.
Just to say to my colleague there, I've been in a 2-week conversation with ChatGPT on programming some Linux computers to do some things. And my experience has been completely opposite to yours, that it's gone through and said, okay, we did this on 4 or 5 days ago, we now need to repeat such and such. Well, that wasn't a question.
I think they must have changed for the better in
This
that
is
respect.
ChatGPT 5.2.
Quite recently.
So maybe they're working.
Thank you for that.
That's my experience. There's a silly question, I suppose, but where does ChatGPT run? Is it got in one place, or is it distributed over many data centres?
That's a good question. I mean, it kind of has to be distributed over many data centres. I'm not that sure of the technical details, but you certainly couldn't run it on one machine. There's just too many users trying to get access to it. So it has to be at least on multiple machines. There are data centres now with tens of thousands of machines. So whether it's all done in one data centre, I would imagine they would distribute it. It's a good idea when you've got a large number of pieces of electronics to geographically separate them.
On your slide, where you had a 13-year-old child with 300 million
Yep.
words, now every step along to the right is roughly going up by an order of magnitude. So you're 3 or 4 orders of magnitude by the time you've got to your latest language model. The 13-year-old child is pretty good.
Yeah.
What age would you put onto your language model? And does this indicate that you've got the wrong approach? Because a 13-year-old child is outperforming you.
I mean, yes, I would agree with that. That is an argument I've made, but it's not accepted by everyone. So a bit of an open question at the moment. But yeah, I agree that whatever the 13-year-old is doing with the data it gets is cleverer than what the large language model is doing, I think.
Yeah, I'm not sure it's level I choose the word because I don't want to put intelligence onto
Right.
AI, but clearly the 13-year-old has something that the AI doesn't have, in that it can do comparable performance with the 300 billion words with thousands of the data. So it's clearly not going through the same mathematical process that the language model is going through to get the answer. It's doing something else.
I would think so, yeah.
The question is, perhaps I can just ask you.
Yeah.
So you're talking about looking back to get the context.
Yeah.
That context could be related to the sentence previously. How does it decide how far to go back and look?
So to some extent, that's an engineering problem. That's how do you allow it to look as far back as it can? So people are now talking about models that have things like 1 million words of context, so a huge context to look back on. You've then got the problem of finding a needle in a haystack. You also have the problem of, we've turned everything into embeddings. That's 1 million sets of numbers. Each embedding is maybe a few thousand numbers, so we're talking about billions of numbers. How do you process that in any way that's efficient? So to some extent, it's an engineering problem of just how do we get that to work. But it's also a problem of is that the right way to solve this problem? You and I are probably not carrying 1 million words of history, precisely memorized history of what's been said to us. And so again, it comes back to this question of, humans seem to do it in some way that's a bit more efficient. And what is that? We don't really know that much. I mean, we know quite a lot about linguistics. How that's embodied in the brain, we don't know too much about. And linguistics is a very fractious discipline where everybody disagrees with everybody else. So that makes it interesting, but I can't say that I have an answer of what is the right way to do that.
Mike, did you have another question?
Yeah, back to the cat.
Yeah.
I'm not sure where it came from in the first place. I can imagine if you're trying to decipher an Egyptian hieroglyphic thing and the word's missing, it'd be quite useful. That it probably was a map. But if you're really doing a piece of homework and you're researching some incident in the past, I don't know, some general met some other general, and there was a cat involved, there will be a definite answer. It did sit on a mat in that case.
Yeah. Would
you still use all this for that, or would you just look at some huge index database and get the answer straight out?
So that predicting the next word is a trick to produce a model that knows enough about English for us to use it. There is some evidence that humans make these predictions. So there are signals in the brain that correspond to, did I expect this word? Is it syntactically expected or unexpected? Is it semantically expected or unexpected? And there's also a theory called predictive processing, which is a general theory of how the brain might work, that says when you are seeing or hearing or understanding language, what you're actually doing is making predictions, and if the prediction is correct, you don't need to do anything. If the prediction's wrong, you just need to send what's wrong about your prediction, and that should make brain processing very efficient. So there is some sort of reason to think that this being able to predict the next word gives you something that is a bit like what the brain's doing, but it's probably not all the brain's doing. It's probably an efficiency trick. And in the case of these language models, you might be learning the right distributions of words and which words occur next to which other words, but maybe you're not learning these syntactic structures, the deep structures that allow you to understand language. Again, that's a controversial topic, but an interesting one.
Sorry, you've answered the first question.
Right.
But I really want to know, what did the cat sit on? Would I use any of this, or would I look for a stored copy of the book or a history book or something?
Do you mean would I do that, or like what's
well,
the?
I'm doing some homework.
Right.
What did the cat sit on that occasion? I don't type it into a language model, do I, or do I?
Some people do. A lot of my students do.
They gave a 150 word answer, which was quite
Is it correct, though? There must be a correct answer in that case.
Are they presuming that LLMs give correct answers? They don't know what correct is.
Exactly.
All right, well, all right.
Which is, have you finished?
Sorry? Well, I mean, there was a real occasion when this cat sat on something. So there must be a true answer somewhere.
I think
Depends if you want an interesting answer or
No,
a
I don't want
factual
interest.
answer.
if you give whatever it is you're querying enough detail about it, if you only ask what did the cat sit on, that's not enough. But if you say when General X met General Y in Albania back in 1397. What did the cat sit on? And surely a large language model should have a pretty high probability of getting the right answer.
Well,
if the answer exists and it's being documented.
if it's in Wikipedia, then it's probably learnt it. But one thing I didn't talk about is, you've probably heard of this, language models have this tendency to hallucinate. So the language model, the model itself makes no distinction between what's plausible and what you're saying, what is true, what actually happened versus what could have happened. It makes no distinction. Those probabilities just say this is probable, it's plausible, and it does kind of memorize things to the extent that things that it saw in Wikipedia get higher probabilities, but it can still come up with something that is just plausible rather than true.
Did you have a question?
Yeah, I have a question. Here you presented something very interesting. I've sort of presented in that way before about the 13-year-old with this many words, and then each of the models that we now generate and use to reproduce the intelligence of ourselves, and it's many, many multiple scales larger to get even the most basic model built to actually generate responses that would be deemed to be a certain level of intelligence. Isn't that revealing what we're doing in the fact that we are brute forcing knowledge about real world, and isn't there then limits to what LLMs actually really can do for us, and is that where world models, which are a hot thing, are going to come in, and is that where you're looking to next, or are you still staying with LLMs?
Yeah, so that's all good points. Yes, world models. I mean, people have talked in AI about world models for a long time. Going back to possibly the beginning of AI, people have thought you need a model of the world. And so that reinforcement learning stuff, very often that involves having a model of the world that you update as you observe what's happening in your environment. So those ideas have been around for a long time. They've not really been deeply integrated into language models yet. And in terms of me, what I'm interested in, so my interest is kind of in the relationship between linguistics and psychology and these models, and how much can these models tell us about the way that humans work, and how much can the way that humans work tell us about what to do with these models. So I suppose world models come into that. I believe that we have a world model in our head. For me, though, integrating the world model with a language model seems like a really difficult challenge, and I would like an easier challenge. So I'm more interested in kind of linguistics and psychology and how that relates.
Right.
Some of the questions which have come up have been, is something true or is it not? The point I would make on that, surely that question has to be answered, is it true in a particular context? So you've got to put a context around it to truth. And it may be 50% true, or 1%, or 99% true. So that's the idea. That leads on to my question, which is, I noticed you had Reddit up on there. Now, I've looked at Reddit.
Yeah.
And it is, it's very amusing sometimes, very amusing indeed. But it's mainly, no, that's unfair. It's often, it is clear fake news.
Right, yeah.
It's fake information. Now, if you're scraping, scraping, a source which is not a reliable source, then you're going to contaminate your large language model. Is that true?
Yes, yeah. So there is a step of filtering the data. It's not something I know an awful lot about, but and I'm not, if we could identify fake news, just easily, then we would, and that doesn't happen. So I'm not sure how successful you can be in trying to filter out the rubbish from Reddit. That is one of the big problems, because you have this extremely data-hungry process. You really can't avoid, scraping up a load of rubbish and worse.
Okay. One thing we do as humans, of course, is that when we're looking on the internet for information, is we will decide for ourselves which sources we trust.
Yeah.
Now, is that process being built in as a parameter in one of the vectors for the large language models. This data is very trustworthy, gives it a higher, increases the probability. This is from a Reddit or whatever, and much lower probability.
I don't know that much about that. Like I said, as far as I understand it, there's some filtering going on. Whether that's based on trustworthiness or whether it's just based on is this the sort of text that we want to learn from or that's going to be useful for learning from. I'm not that sure.
There is a bias to data. So, for example, Grok gives a completely different answer compared to ChatGPT because they've put a different trust level approach in that. And you've got to really think about it as well that we as people actually aren't very good at identifying false information, because we maybe feel that we can identify false information, but there are many people in this world who we can clearly see do not have that filter.
Yeah. Their objective is to sell advertising. So whether the answer is correct, false, true, indifferent, if it sells advertising, it's achieved its objective.
At the back, perhaps.
Has anyone ever compared the process with what happens with the way that children learn to talk? If you take a 6-year-old child, for example, they're pretty good at talking by that age. They know nothing about nouns or verbs or formal grammar or anything like that. And they haven't even been through a process. They just soak it up somehow. I just wonder whether that can provide any insight into what the language models are doing.
People are asking these questions and looking at are there commonalities, are there differences? But it's not a core concern of, say, these big companies like OpenAI. But yeah, so that's the sort of thing that I'm interested in. What can we learn? There's all sorts of interesting things happen as children learn language that don't entirely make sense, but...
it's a miraculous process.
Yeah.
They've had by 6 years old, they've had very little formal training. They just do it.
Yep. Yeah, so I mean, there's the famous Steven Pinker book, The Language Instinct, that it's an inbuilt drive that, human beings are driven to learn and speak languages. I mean, I'll go off on a tangent for a bit. One of the most interesting facts is that children don't even really need adults who are really competent, rigorous speakers of a full language. So it particularly happens in communities where slaves have escaped their masters. And these communities very often do not have a shared language. So they might be drawn from West Africa, from East Africa, from North Africa. And there isn't a coherent single adult language. So the adults speak what's called a pidgin, which is like a gluing together of some basic things. The children create what's called a creole. They create a language from nothing, and it has all the complexity of any other language. And they create it by playing, as the way children do.
Yes, I suppose it's a sort of, I know we want to conclude in a way, but the question is, which is probably beyond this talk, which is, the uses to which AI is put and whether AI is reliable in those uses. And if I should be allowed to give one thing which I think I got from Reddit,
right,
which was there are all these Epstein documents, 6 million or 3 million or depending, whatever it is, and they have been redacted.
Yep.
And one of the redactions, which one wonders whether it was done by AI, but it was certainly, if it was done by AI, it was done by uncorrected AI, was that the word don't was actually redacted because it looked like D-O-N-T, miss out the apostrophe, Donald Trump.
Right.
And so it was redacted.
Conspiracy theory.
Right. Okay, well, we better let everyone get home and hope it's not raining. Last October, we had a talk that used about the simplest AI application, just a classification of handwritten digits, you know, as simple as you can get. I can understand that. You know, I thought that was okay. Jeff tonight has taken us to a whole new level in thinking about how large language models in particular operate and what they can do. I think more research is needed on my part. So thank you very much, Jeff.
Yeah, thanks for having me.
Interesting talk.
Thank you.